Okay, the final section of chapter 6. This is where we get into, I guess, a bit more real world. A linear economic model. So, give you a little background story. There it is. Moving on. Single good economy, example 1. So, consider an economy with a single good, lumber. Only one, and when I mean good, I mean like product. I guess something for sale or to buy. It only has a single product, a single good, lumber. We suppose here, and in the general case as well, that some of the good being produced is consumed in the production process. For this example, suppose that 0.2 unit of lumber is consumed in the production of 1 unit of lumber. Finally, suppose we have an order, I guess typo there, for 10 units of lumber. How many units of lumber must be produced to fulfill this order? So think of it like we have somebody who wants to buy, a bunch of 2x4s or whatever. And so we cut down some trees to produce these 2x4s, but in the process, some of the wood from the tree gets consumed or used up. And we don't end up using all the wood from the tree. We only use up some of it to make these 2x4s for this person. So we're trying to produce 10 units of lumber for our customer, but we can't just cut down 10 trees and say that's 10 units of lumber because some of that tree gets, cut or used in the process. So we have to figure out how many trees or whatever, however many units do we need to really, harvest to get a net of 10 units of lumber, if that makes any sense. And these examples get a little bit more elaborate as we go on, but the understanding of this is important because it's going to be used throughout. So think of it like this. For this problem, how are we going to find out how much lumber we need to harvest in order to make 10 units of lumber? If every unit of lumber we get, 0.2 of it is wasted or consumed in the process. So think of it like this. If 0.2 units of our lumber is used up every time we find 1 unit of lumber, then basically every unit of lumber we find is 0.8 units of lumber, right? I find some lumber, but I can only use 0.8 of it because 0.2 of it is disappearing, remember? So 0.8 is how much of it that I can use. I can only use 80% of what I'm harvesting for my final product. So 0.8 per however many, we need to try to find how much lumber do I need to consume to make my 10 units of lumber. So my goal is 10 units of lumber. I use 0.8 every time I try to use 80% of it. So how much do I need to really find in order to make 10 units in total? So that's my simple equation there. 0.8 times however much I need to find to equal 10 as a net value. So simple equation enough to solve. We divide by 0.8 on both sides. And we end up with x equaling, what is it? 12.5? I forget. Yeah, 12.5. So basically, in layman's terms, I need, to cut down 12 and a half trees to make 10 2x4s. I can't cut down 10 trees to make 10 2x4s because some of that wood gets used in the process. So I need 12 and a half trees so that all that extra wood that I'm wasting, I've set aside, and I end up at the end of this with 10 2x4s, 10 of that exact unit that I was trying to get. Okay, hopefully that makes a little bit of sense. All right, suppose we have an economy with 2 goods. Okay, economy with 2 industries, each of which produces a single good. So, and suppose the economy operates over a specific time period, like 1 year, for example. Consider a situation where each of the industries may use some, or again, another typo should fix, or both goods in the production processes. For example, in the 2 goods, if the 2 goods are lumber and steel, so let's say we have a lumber manufacturing company and a steel manufacturing company. The people who produce lumber are going to use some lumber and some steel in the production to make lumber. And same thing for steel. The people who are making steel might use up some of that steel and some lumber as well, just to make some of their units of steel. Okay. So if the two goods are lumber and steel, then some lumber and some steel are used in the production of lumber, and likewise both goods are used in the production of steel. Let x1, this is just our notation, okay? Let x1 be the amount of good 1 produced in this economy, and let x2 be the amount of good 2 produced. Okay. So now we see where the matrices come into play a little bit here. When we have a matrix, A11, A12, A21, A22, what these values are going to represent is A11 is going to represent the amount of good 1 used in the production of good 1. So for example, if we say lumber is good 1, then this is how much lumber we use to produce 1 unit of lumber. A12 will be the amount of lumber we use to produce steel. So this will be how much lumber we use to produce steel. So again, this is how much lumber is being used. This is how much to produce lumber. This is how much to produce steel. And then likewise for the second column or second row, A21 is the amount of good 2, so the amount of steel used to produce a unit of lumber. So this is how much steel we use to produce lumber. And A22 is how much steel we use to produce steel. So very interesting layout, but you can sort of see how these matrices are going to be built. We're going to have a row that represents the production of lumber and production of steel. And then we're going to have the columns representing the product of lumber and the product of steel. So production and product. Okay, very interesting. Interesting stuff. All right, external demand. Not only to add to this matrices a little bit, though, and make it a little more complicated, but here we go. By external demand, we mean an order for goods, kind of like the 10 bits of lumber that was asked for us in example 1. That's our external demand. We have a customer who wants a certain amount of wood or a certain amount of lumber, a certain amount of steel. We need to figure out how much wood and steel I need to collect in order to fulfill this person's demand. Okay. So this gets really mathy. So bear with me a little bit, but it gets rather simple once we get into the actual matrix. But this is sort of how the matrix is built, if you will. This is sort of trying to explain how we write our matrices in the future. They won't be that difficult to write, but maybe, I don't know. We'll have to find out. Since it takes A11 units of good 1 to produce 1 unit of good 1, so this is kind of like, you know, how it took 0.8 units of good 1 to produce, or 0.8 units of lumber to produce a unit of lumber. We assume it takes 0.A11 x1, which is units of good 1 to produce x1. So this is kind of like going back to our example 1. This number would kind of be the 0.8. Because in example 1, we said that, 0.2 of our lumber was used up in the process. So 0.8 of it was good to go. And then this is the 0.8 times x. Because remember, our equation was 0.8 times x equal to 10. Well, 0.8 times x is the total amount that we need to harvest to fulfill that demand. So we've already done this math before. This is just another funny way of communicating it. That weird sentence. Also, we assume it takes A12 x2 units of good 1 to produce x2 units of good 2. So I don't have an example for this yet, but if we had lumber to produce steel, let's say our steel production needed 0.7 units of lumber, then 0.7 units times x can help fulfill that 0.7 units of however much lumber we need in order to produce however much steel we need to make, and so on and so forth. Now, D1 is going to represent the units needed for external demand. So D1 just represents like that number 10 from before, like how much of it we're asked to make. So there's an equation we get from all of this. X1, which is, remember, our kind of like our product. The what do I call it? The amount of good one produced. The amount of good one produced is going to depend on how much of that good we use to make it and how much of the other good we used to make it, plus the demand for it. And likewise for our steel. The production of steel is going to be how much wood we use to make the steel, how much steel we use to make the steel, and plus our demand for it, because we need to know how much in total there is that we're going to need. Okay, so remember, this is a total amount of steel equals how much wood was used to make the steel, how much steel was used to make the steel, and then the demand for how much steel that we need to make. And it sounds kind of odd at first, but once we get into the math, you'll get it. So here are these matrices. A is what we're going to call our technology matrix. This is basically the most common, and usually given to you, or it's pretty easy to make this technology matrix. But this refers to how much wood how much lumber is used to make lumber, how much lumber is used to make steel, how much steel is used to produce lumber, and how much steel is used to produce steel. It's sort of the consumption process. X is the production schedule. So this will be, how much lumber and steel we end up harvesting. And then D is going to be the demand. What are people wanting? How much do we need to produce in order to satisfy their need? So to sum up what all these different letters and variables mean, again, I've sort of outlined it here already, but it's there one more time for you to understand. One, if you want to think of lumber and steel again, think one refers to lumber and two refers to steel. So lumber making lumber, lumber making steel, steel making lumber, steel making steel, total amount of lumber, total amount of steel, demand for lumber, demand for steel. But now I think it's time we start getting into some of the math. So there's a formula, that equation that we just mentioned earlier from all that interesting information. Here's that formula. X, remember, which is our production schedule, equals our technology matrix, which is our, I guess, how much we end up using, times X again, our production schedule, plus the demand, plus however much people are asking for us to make. But what's important is that there's variations of this formula. And they're outlined here, but let me explain where they come from. So X equals AX plus D. So let's say I wanted to have D all by itself. Well, then I would subtract this right here on both sides, and I would have that cancel out, and I would have D equal to X minus AX, which, because X is in both of these, is the same as X times 1 minus A, which 1 is the same thing as I, the matrix I. So that is one of those formulas. That's what is referenced here. This is the same formula, but this is the same formula used if we want to know the demand specifically, right? So if we're asked to find the demand, we'll probably use this formula, or this version of the formula, since this is the one that has demand all by itself. But other versions of this formula, let's say you wanted to get X by itself. I'm trying to remember how we did that. Well, if you go back to that one we just made, the I minus A times X equal D. If we want X by itself, then we need the inverse of this. So if you can find the inverse of this, that would cancel it out. A minus, or 1 minus A inverse would cancel out, but you'd have to do that to this side as well. I minus A inverse. If you find the inverse of the I minus A, then you have the formula for X. So if you're looking for the production schedule, you'd use this variation of the formula. Complicated stuff, but it's all right. It gets better. All right, so example. Let's actually get to work now. Consider a Leontief. I don't know how to pronounce it, but I'm just going to say Leontief or whatever. Input-output model for an economy with two goods, steel and coal. Suppose 0.1 unit of steel and 2 units of coal are required to produce a single unit of steel. And 0.3 unit of steel is required to produce 1 unit of coal. Find the technology matrix A. This matrix is not that complicated or that tricky to figure out, honestly. I think once you see it, it'll make sense to you. So remember A11, A12, A21, and A22. Let's try and make that look a little bit better. So let's say 1 is for steel and 2 is for coal. So this is referring to how much steel to make steel. Well, we'll use 0.1 unit of steel in the production of 1 unit of steel. So 0.1 is that value there. That's how much steel is used to make steel. A12, this is how much steel to make coal. And you can see it takes 0.3 units of steel to make 1 unit of coal. So 0.3 units of steel to make 1 unit of coal. Now 2.1 is how much coal to make steel. So it's 2 units of coal to make a unit of steel, as we can see outlined there. And then the last one is 2.2, which is how much coal to make coal. Now, if you look at this, there is no coal needed to make coal. It says 3 units of steel is used to produce 1 unit of coal. It doesn't say any coal is produced at all, or any coal is used in that process. So 0 coal is needed, apparently. So there is your technology matrix, typically referred to as matrix A, as indicated from previous things. Technology matrix, matrix A. It doesn't have to be 2 by 2, but it is 2 by 2 because we're talking about 2 goods, an economy with 2 goods in it. If it's an economy with 3 goods in it, it would be 3 by 3. An economy with 4 goods in it would be 4 by 4, so on. But this economy has 2 goods, so it's 2 by 2. So this is our technology matrix. That's example 2. Again, I think it's very easy to do when you think of 1 and 1, 1 and 2, 1 and 2 as being the goods. Steel to make steel, steel to make coal, coal to make steel, coal to make coal. I think that makes a lot of sense. It makes it easy to fill out because all that information is already given to us. It's just a matter of making sure it's in the right part of that matrix. Example 3, consider a Leontief, again, probably pronounced wrong, input-output model for an economy with 2 goods, steel and coal, and technology matrix is this. Note that that's the same technology matrix we just found from the last problem, so we're kind of continuing that problem here. Suppose that the external demand vector is 12, 3. So remember, this is the demand vector. This is the matrix D. Find the production schedule which meets this demand. So if we go back to our formulas, we are looking for a production schedule. We're looking for X. X is our production schedule. So I'm going to use this version of that formula since it already has the X by itself. I think that'll be easiest. So X equals I minus A inverse times D. So I already know what the D matrix is. It's 12, 3. But now what I really need to do is find I minus A inverse matrix. So I already know what A is. So I, remember, is the 1, 0, 0, 1. And I need to subtract A from it. 0.1, 0.3, 2, and 0. I think this is probably easier to do by hand since when you subtract, you just subtract likewise around. So 1 minus 0.1 is 0.9. 0 minus 0.3 is negative 0.3. 0 minus 2 is negative 2. And 1 minus 0 is 1. So this is 1 minus A, but I need the inverse of that. So that's where I will use the calculator. I'm going to type this in the calculator to try to find out what the inverse of it is. So let's go to our calculator. I'm actually going to end up saving this on the screen. Keep it. Calculator. Remember second, and then the inverse button takes us to matrix. I'm going to go to edit, and I'm going to edit this. It's going to be a 2 by 2 matrix. And our matrix that we just said was 0.9 and negative 0.3, negative 2, and 1. So that's matrix. I need to figure out what the inverse of that is. So let's select that matrix. Matrix A is what I just had. Let's put inverse on it. And the inverse is this. I'm going to, obviously, let's convert that to fractions because it'll look a little bit better. So math, enter, enter. We have 10 thirds, 1, 20 thirds, and 3. So back to this. My inverse matrix that I just got was 10 thirds, 1, 20 thirds, and 3. So there you go. So all I got to do now is take that inverse matrix that I just got and multiply it with the D matrix, the 12, 3 matrix. I just need to type this in the calculator. That is all. What I probably should have done is put that 12, 3 matrix in earlier, because then I could jump ahead and save myself a little time, but I didn't. It's okay. So let me go back to calculator. I need to put this. Let me keep that answer, by the way. That's important. But let me go back to my matrix and let me input this demand matrix in. Crap. That's not what I wanted. I always forget to go to the edit thing. Nope, wrong thing. Edit in for B, and it's a 2x1 matrix. So don't forget that. And it was 12, 3. All right, so now the calculator knows the matrix. I'm going to go back. And I'm going to take the answer because I need that answer, right? That 10, 3, 1, 23, 3 thing. I'm going to choose that. So second and negative gives me that answer, that previous answer, that matrix. And I need to multiply that matrix with that demand matrix that I just typed in, which I typed in as matrix B. So I'm going to select matrix B. So I'm doing that inverse matrix times the 12, 3 demand matrix, and I get 43.89, which is my answer. That is my production schedule. So basically I need 43 units of, steel, and 89 units of coal to fulfill my request for the demand of 12 and 3. Interesting, if you think about it. Very inefficient economy, but it's okay. Or inefficient, if you use words properly. It's confusing at first, I'm sure. But hopefully in class I said it better than I said it in the video. Example 4, suppose an economy has 3 goods, which of course makes a 3x3 matrix: cement, electricity, and steel. The technology matrix is already made for us. So just to translate, this would probably mean if cement is 1, electricity is 2, and steel is 3, then this is 1, 1. So this is how much cement is used to make cement. This is how much electricity is used to make cement, and this is how much steel is used to make cement. And then the second one would be, this is how much cement is to make electricity, this is how much electricity is used to make electricity, and this is how much steel is used to make electricity. So that's a simple translation. And of course, steel to make cement, steel to make electricity, and steel to make steel. But it's besides the point. Let's get back to the math though. In A, which is this matrix, the first row corresponds to cement, as we mentioned. That's how much cement is used to produce products. The second is electricity used to produce products, and the third is steel. Find the external demand D, which will be met by the production schedule X. So I have my A and my X. I'm looking for demand. So demand, if I go back to my formulas, demand was this matrix here, or this version of the formula, I minus A times X. No inverse, right? Just I minus A times X. Let's go back to my problem. So I minus A times X is going to equal the demand matrix, which I'm trying to solve. Now I already know X is 30, 20, and 40. But what's I minus A? So remember, I is just, in this case, a 3 by 3 matrix. I is just 1, 0, 0, 0, 1, 0, 0, 0, 1. That is your I matrix, and you're subtracting A from this. So you 0.2, 0.6, 0.2, 0, 0.1, 0.4, 0.6, 0, and 0.3. So again, 1 minus 0.2 would be 0.8. 0 minus 0.6 would be negative 0.6. 0 minus 0.2 would be negative 0.2. 0 minus 0 would be 0. 1 minus 0.1 would be 0.9. 0 minus 0.4 would be negative 0.4. 0 minus 0.6, negative 0.6. 0 minus 0 is 0. And 0 minus, or I'm sorry, 1 minus 0.3 would be 0.7. You could probably do that in the calculator, but I think you guys know how to subtract. It's probably pretty easy to do that, in my opinion, but it's all good. So if I take this matrix times the production schedule matrix, I will get my demand matrix, my answer. So all I'm going to do is type this in my calculator now. Let's go to my calculator. Type this all in. So let's input these matrices in real quick. So go to second matrix, edit. I need a 3 by 3 matrix, so 3 by 3. And we got, forget, let's go back to it. 0.8. Yeah, 0.8, negative 0.6, negative 0.2. So 0.8, negative 0.6, negative 0.2. Then it was 0, 0.9, negative 0.4, negative 0.6. Let me double check that. Yeah, 0 and then 0.7. 0 and 0.7. So have that in there. That's matrix A. I put that in for matrix A. I'm going to put this, I need to put the demand one in. So that's the 30, 20, and 41. So let's go back. Matrix. Let's put a new matrix in here. Let's put this in for matrix B. Let's edit that. We need to make it a 3 by 1 matrix. And I believe it was 30, 20, 40. So 30, 20, 40. So now I'll just let the calculator do the multiplication. So matrix A times matrix B. So select those. Matrix. I need the first one. Multiply it with matrix, the second one. And we get, why did I hit that? Why did I hit that button? Okay. There we go. Enter. There you go. 4, 2, and 10 would be your answer. So the calculator can do a lot of the work for you. There is some stuff you have to do by hand. You have to be very aware of the formulas as well. It gets easier the more you practice, and we'll certainly practice a lot. But yeah, I know it can be kind of daunting at first, but don't be too afraid of it. I promise it's not that bad. Over time, it gets easy as it goes. Example 5. Consider an economy which has 2 goods, lumber and steel, and suppose the table gives the goods required. So basically, this table is already our technology matrix. So yeah, let's find the associated technology matrix A and determine whether I minus A has all positive entries. So we're not really doing any math. We're just trying to answer this question: is I minus A have all positive entries? And let's find out. matrix A, it's essentially this matrix right here. Matrix A is 0.6, 0.6, 0.5, and 0.2. The question is I minus that, which remember I is 1, 0, 0, 1, minus this A matrix, does it have all positive entries? And the answer, I believe, is no. 1 minus 0.6 is 0.4, but 0 minus 0.6 is negative 0.6. There you go. You've already got a negative entry. 0 minus 0.5 is negative 0.5, and then 1 minus 0.2 is 0.8. So both these values are negative. So no. The answer is no. They're not all positive. No. I don't know if that's all the question was asking, but it seems like it was all it was asking. All right. Write the system equation as a matrix equation and solve. We can actually just use this in our calculator. We've done these problems before in the calculator, and you can get the answer that way, but let me show you how this translates into a matrix. This is what I didn't really show you the first time. So I don't know how to explain this, but I'll kind of just write it down and then try to work from there. So this is going to be, this is the matrix 2, 3, 5, negative 1 times the matrix x, y equal to 8, negative 2. And the reason this translates into this is because think of your matrix multiplication. If you did your matrix multiplication, you would do the first row by the first column. So it would be 2 times x and 3 times y. And you'd add them up and you would get the first row, first column number here, which is 8, which is of course, the exact same thing as you can see that equation is. And the second one, the second row by the first column would be 5 times x, would be negative 1 times y, which would be plus negative y or just minus y, equal to the second row, first column number here, which is negative 2. And as you can see, that is that equation. So this is the sort of matrix version of writing that system out. It tends to be pretty simple. You can see that this matrix A is very similarly lined up to that. 2, 3, 5, negative 1, 2, 3, 5, negative 1. It's all sort of there as it should be. It's just you separate the x and y into its own matrix because you multiply the row by the column. So this will be with the x, and this one will become with the y. This one will be with the x, and this one will be with the y. So the x and y becomes its own matrix, and it equals our solution matrix, right? So the question is, let's find out x and y. So if we're going to use this using matrices rather than the other way we've done in the calculator, it's straightforward. All I need is the inverse of this matrix. If I call this matrix A, then I need to find out what the inverse of that matrix is so that it would cancel out. And I'd have to multiply that matrix inverse here. So let's find out what the matrix inverse of this is, and we'll multiply it with 8 and negative 2. And we'll have our answer for x and y, and we can check that as well. I'm going to keep it. So let me go ahead and type this all in my calculator. Clear that. Go to edit. We're going to make a 2 by 2 matrix here. And that 2 by 2 matrix is 2, 3, 5, and negative 1. So 2, 3, 5, negative 1. All right. I'm also, while I'm here, going to put in my solution matrix, which was that it was a 2 by 1, and it was, what was it, 8, negative 2, I think? Yeah, 8, negative 2. So I'm going to go ahead and type that in here while I can. So all I need to know is what the inverse of matrix A is. So let's get out of this. I'm going to select that matrix, matrix A. I'm going to find its inverse. Okay. Fancy. Great stuff. I can probably convert it into fractions. I don't think I need to, but I'm going to just see what the heck it looks like as a fraction. So that's fine. And now I need to multiply that matrix. So I'm going to take that same matrix I just got, and I'm going to multiply it with that 8, 2 matrix, which we put in here already as in as matrix B. So we're going to select that. And there we go. I feel like that's wrong, but maybe I just made that system up on the spot and I'm really bad at it. So let me check this real quick. Let me check. Using the old-fashioned way. I don't think I actually checked these the first time. I don't think that's right, but we'll see. Two equations. Two unknowns. And we had 2, 3, 5, -1. Oh, crap. That's doing it wrong. Actually, I think that was supposed to be negative, but we'll fix it. Yeah. All right, so it worked. It's the same answer, right? 2/17 and 44/17. I had just assumed that maybe I had made a problem that used, cleaner numbers than that, but apparently not. But yeah, 2/17 and 44/17. You can see that's how we did it before, typing in the calculator, but using matrices, we got the same answer. It's kind of nice to know that it works out. But yeah, I was expecting it to be, I guess, more friendly than that. And you can do the same thing with this one. If you want to write the matrix out, so this would be, I think you really need practice more on just writing these matrices out. So this would be a 1, 1, 1. I'm just going to write matrix A first. There's no x value here, so it would be 0, and then 2, 5. And this one would be 2, 5, -1. So 2, 5, -1. Times your x, y, and z to equal the 6, -4, and 27. So again, let's go ahead and let's do this real quick. It shouldn't take too long. This will be matrix A right here. But again, I need to figure out what the inverse of that is and multiply that with this solution set. So let's type it all in the calculator. So let's go back to our matrix. We're going to edit. We're going to make this a 3 by 3 matrix. And I believe it was 1, 1, 1. I know the first one was 0, and then 2, 5, 2, 5, and also 2, 5, -1. So 2, 5, -1. So there's that original matrix. I'm also going to go ahead and put in the solution version, which is a 3 by 1 matrix, so 3 by 1. And the solution set was 6, -4, and 27. So 6, -4, 27. Right? Right. Just making sure. All right, so same thing we did before. Now that all the matrices are in there, let's just go ahead and do the math. I need an inverse of my first matrix. So I'm going to select my first matrix. I'm going to select the inverse function and find its inverse. So there it is. You can see it's cut off as a little arrow. I'm going to go ahead. You don't have to do this part of it, but I do want to put it in the fraction form just so I can see it a little better. That's the inverse matrix. Now I'm going to take that matrix. So hit second negative, it gives me that answer, that matrix, and times it with the solution set matrix, which is that 3 by 1 matrix. And we're going to get 5, 3, -2. And if you go back, so that's your answer, 5, 3, -2. That's your x, y, and your z. 5 is x, 3 is y, and 2 is -2 is z. That same exact system should work the old-fashioned way. I want to do this just to check, I guess, just to prove a point. But yeah, you can probably fast forward and get there for me, but it's all good. 1, 1, 1 equals 6. 0, is it 5, 2 or 2, 5? 2, 5. 2, 5. Oops, not 2, 25. 2, then 5 equaled -4, and then 2, 5, -1 equaled 27. All right, and we solve it. It should be the same values, 3, 5, 3, and -2. So matrices do work. It's the exact same thing as this, actually. But the properties and the rules of how these matrices work, it's very important that we understand that and those connections and how to solve those problems using matrices and not just this version of the calculator. So I'm going to stop it there. That's the entire section, chapter 6. I would say more than anything else, I want you to be able to translate this system into this matrix setup. If you can do that, forget the whole solving thing. We can solve it later, but being able to rewrite this into this is a big deal. So make sure that you're good with that, and I'll see you later. We'll have a quiz or test coming up on this, and yeah, good luck. Bye.